All right, let's get right into it. At the very heart of how we manage, well, all the world's information, there's this huge tug of war going on. It's a constant battle between two big ideas. Should we keep our data perfectly neat and organized, or should we be able to get to it lightning fast? And trust me, this isn't just some techie problem. It's a strategic fight that shapes pretty much everything, from your online shopping cart all the way to the future of AI.
I mean, think about this for a second. We've all been there, right? You go online, you update your shipping address on some website, but then the next promotional flyer shows up at your old apartment. It's annoying. But what you're seeing is a tiny real-world symptom of a massive data problem. It's a little ghost in the machine, a sign that data is out of sync, and it's something engineers have been battling for decades.
So, to really get why we needed a solution, you got to look back at the beginning, back to the Wild West of early databases. In those days, data was just messy. And duplication? It was everywhere. It was total chaos, super inefficient, and it created some seriously gnarly problems.
And this, right here, this is a perfect picture of that chaos. Just imagine a single giant spreadsheet for an online store. For every single item a customer buys, you'd store their name, their full address, and their phone number all over again. So, one customer makes 10 orders, that's 10 separate copies of their personal info. You can already see how this just eats up storage, and, way more importantly, it's just asking for mistakes.
And those mistakes? Oh, they have names. They're called anomalies, and they're basically the villains of our story. First, you have an insertion anomaly. That means you literally can't add a new customer to your list until they've actually bought something. Weird, right? Then there's the update anomaly. That's our address problem. If you have to change it in 10 different places, you're probably going to miss one. And the deletion anomaly is honestly the scariest one. If a customer cancels their only order, you might accidentally wipe their entire existence from your database. So the main takeaway here is this wasn't just messy, it was fundamentally broken.
So into this digital chaos walks our hero, a British computer scientist working at IBM named Edgar F. Codd. He looked at this absolute mess and came up with a revolutionary idea, a formal set of rules to bring logic and order to the world of data. He basically declared a war on redundancy.
And his weapon of choice in this war was something called normalization. Put simply, normalization is just a step-by-step process for organizing your data to get rid of all that duplication. So, instead of one giant, messy table, you break everything down into smaller, related tables. The customer's address gets stored once, the order details get stored somewhere else, and you just link them together. One change in one place, and it updates everywhere. Genius.
Now, this whole thing didn't just happen overnight. It wasn't some single aha moment. It was a formal academic process that played out over several years. In 1970, Codd gave us the first normal form, or 1NF. A year later, he laid out the second and third normal forms, and each new step added even stricter rules, systematically squeezing out the duplicates and making the whole database more logically consistent.
We don't need to get totally lost in the weeds here, but the core ideas behind it are actually beautiful in their simplicity. Step 1 is just, each little box should only hold one piece of information. No stuffing 3 phone numbers into one field. Step 2, make sure that all the data in a row is related to the entire unique ID for that row, not just a piece of it. And Step 3 cleans it up even more, getting rid of any data that's hanging on to other non-essential fields. See? Each step is just a logical cleanup, making sure every piece of data has one and only one true place to live.
So, Codd's war was a massive success. Databases became way more reliable, consistent, and much better with storage. But, victory always comes at a price. This new, beautifully organized world had an unintended side effect, a new kind of bottleneck that nobody really saw coming. Remember how we split everything up into all those small, neat little tables? Well, to get a complete picture, like, say, a customer's name, their address, and all of their orders, the database now has to stitch all that information back together. This process is called a join. And look, joining 2 or 3 tables, no big deal. But joining 5, 10, maybe even more tables to create a complex report, that can get incredibly, painfully slow. The very thing that made writing data so safe was now making reading data slow.
And that, right there, became the new reality. The battle wasn't just about order versus chaos anymore. It turned into this sophisticated balancing act. What do you prioritize? Do you want perfect, bulletproof data integrity, or do you want the speed and efficiency of getting answers from your data right now?
So you can probably guess what happened next, right? This performance problem led to a sort of counter-movement, a rebellion, if you will. Developers and engineers started asking a very practical question. What if we intentionally broke some of COD's perfect rules, but did it strategically, just to get our speed back?
And this new idea was called denormalization. Now, this is a really crucial point. This is not the same as just going back to the old, messy, unnormalized way of doing things. No way. Denormalization is a deliberate, strategic choice. You start with a clean, normalized database, and then you strategically reintroduce a little bit of duplication, like copying the customer's name onto every order record again, specifically to avoid those slow, expensive joins.
So why on earth would you do this? Well, the benefits are all about one thing: speed. By pre-joining some of your data, you boost your query performance like crazy. You make retrieving data simpler because your app can just grab everything it needs from one place. And it's an absolute game changer for things like reporting dashboards, where you need to calculate totals and averages super fast without slowing down the main system.
So, all of this brings us to today. The war is over. You could say a peace treaty has been signed. We now live in a world where these two opposing forces, normalization and denormalization, are actually used together as part of a really smart data strategy. It's no longer about which one is better. It's all about using the right tool for the right job.
And you can see the whole trade-off laid out perfectly right here. With normalization, you get amazing data integrity and you're super efficient with storage, but you pay for it with slower queries. On the other hand, denormalization gives you those lightning-fast queries, but it uses up more space, and, crucially, it creates a risk of data getting out of sync that you have to actively manage. It's a classic engineering trade-off. And here's how that actually plays out in the real world. Think about your day-to-day systems, the ones that are constantly processing sales, updates, and transactions. We call those OLTP systems. They're almost always normalized because you absolutely need that integrity. But then you have the systems used for business analytics, big reports, and training AI models. We call those OLAP systems. They're often denormalized because for them, the speed of analysis is everything. Now, what's really changed the game recently is technology. The cloud makes storing all that duplicate data incredibly cheap, which takes away one of the biggest downsides of denormalization. Cool tech like Change Data Capture, or CDC, can automatically see a change in one place and instantly update all the copies to keep everything in sync. We even have AI now that can look at how data is being used and predict the best way to denormalize it for peak performance.
And all of this brings us to a final, really interesting question. For decades, perfect, pristine, totally normalized data was the holy grail. It's what everyone aimed for. But now, as we move into an era dominated by AI and machine learning, which just love huge consolidated data sets, is that perfect structure still the goal? Or is a little bit of strategic messiness, a little bit of planned redundancy, actually a feature that helps us get speed and insight rather than a bug we need to fix? The great data debate, it seems, is far from over.